first thing I need you to discuss at your pod is how do you find the area of a trapezoid? That's a trapezoid, minus the arms and legs.
So then wouldn't it just be based on
It's two.
All right, who thinks they have it? Joe? Thoughts? Not sure?
Not sure.
He is right. He is right. 1/2 base 1 plus base 2. Okay. Now, we are going to use that to help us figure out kind of a shortcut later. But as we've been doing our rectangles, right, at least for sure with the right and the left endpoint, they either hang way over or they hang way under. Now, with our midpoint, we got a little bit better. With each rectangle, a little bit hung outside the curve, a little bit was under the curve, right? Well, to get an even better approximation, we can use trapezoids, okay? Let me draw you a picture to the best of my ability here. So let's say we're finding the area under this curve, right? If we split this up, okay, then our trapezoids, we would use the left end point, the right end point, and connect those to make a trapezoid. The left end point, right end point, connect them to make a trapezoid. So do you see how those fit just a little bit better under the curve? Okay, there's a little bit less space that we are using up here. Okay. Now it's going to be a little bit of an under approximation for if we are concave up, a little bit of an over approximation if, concave down, a little bit of an over approximation if we're concave up, but it's going to fit a little bit better than a rectangle, okay? So much like our rectangles, we're going to do the same thing where we have to determine the number of trapezoids we're going to use. We have to figure out, instead of the width, there's not like a width of a trapezoid. Our width is now going to be the height of the trapezoid, which we'll use the same way. Okay. And then our function values will tell us the length of the bases of our trapezoids. I'll draw you a picture there so you can visualize what those trapezoids are going to look like, okay? We like regular isosceles trapezoids, right? We like those. That's what we think of. But it doesn't have to be isosceles to be a trapezoid, okay? What's going to happen is one of those sides is going to sit on the x-axis, and that's going to be our height, all right? And and then the bases are the different lengths based on the function value. Okay. So we're going to have to find the area of each of our trapezoids, add them up, bam, we have our area. Okay. Now for right now, we are going to find the area of each trapezoid individually, but then we're going to see if there's any way we can like condense this into a little bit easier way to remember than 1/2 height times base 1 plus base 2 plus 1/2 height times base 1 plus base 2 over and over and over again. Okay. So go ahead and get out your foldable, and the trapezoid one is at the very bottom. Okay. So as we did on Friday, delta x is b minus a over n, which is 1/2. Okay. So if we are talking about this first trapezoid right here, then we're going to take 1/2 times the height of our trapezoid, which is delta x, times the length of each of our bases. Well, as I told you, our bases are going to be the function values. So since this first trapezoid stretches from 0 to 1/2, the first height would be the function value at 0. The second, base would be the function value at 1/2. Okay. Here's our next trapezoid. Our area, we take 1/2 times the height times the sum of the bases. Since this trapezoid stretches from 1/2 to 1, our first base has a length of the function value at 1/2. Our second base is the function value at 1. Okay. Next trapezoid, 1/2 times the height times this trapezoid stretches from 1 to 3/2, so our bases are the function value at 1 and the function value at 3/2. You're tired of writing this, right? Okay, our last trapezoid, 1/2 times the height times our bases. Well, our trapezoid stretches from 3/2 to 2, so our bases come from the function value at 3/2 and the function value at 2. Okay, that's a lot to write, and that's a lot to think about every single time. Okay, let's look at this and let's talk about some similarities in every single trapezoid that we found. First of all of them start out with 1/2, right? And all of them have the height. Do you agree? So could I take 1/2 times the height and factor it out? Yeah, that would be way easier. Okay, so let's do that. Now I want you to look at the bases that we add together. Observations.
Okay, so it's the first and last one.
Okay, so we have to use all of our interior bases twice, right? We have to use the base at 1/2 twice. We have to use the base at 1 twice. We have to use the base at 3/2 twice. But the ones on the outside, we only have to use once, right? So our first base we use once. Our next bases we have to use twice. And our last base, we have to use once. Okay, so it's going to be like this every time. Instead of setting up however many trapezoidal area formulas we need to, we can just write, and we'll rewrite this on a here soon after we find out this actual value. 1/2 times the height times base 1 plus 2 of base 2 plus 2 of base 3 plus 2 of base 4, all the way until we get to only 1 of the last base. Okay, so let's go ahead and figure this out here. So f of 0 is 0. F of 1/2 is 1/4. F of 1 is 1. F of 3/2 is 9/4. And f of 2 is 2. Okay. We get those function values by plugging in the x to the function itself. Fraction form 11/4, which is 2.75. Okay. If you recall Friday, maybe, I don't remember, but I did tell you that the actual area under this curve from 0 to 2 is 8/3. If you look at all 4 of those values, the trapezoidal area is going to be the closest to 8/3. Okay. Okay. All right, so let's go ahead and write down a specific rule, okay? And so whether you want to write this down on your blue sheet or your notes, that is up to you, okay? But if we have the trapezoidal we're using trapezoids for our approximations here. Okay, so we're talking about 1/2 times the height. Okay. If we're stretching from A to B, then our function value at A is our first base, and our function value at B is our last base. Okay. And every base in between, we need how many of? 2. Oh, that's the second time I've done that today. Well, at least that one's still open. Okay. Bear with me. In that missing spot, so we have area is 1/2 times the height. Okay. Okay, so this is pretty general, right? I don't know how many trapezoids you're gonna sum together. It may be 3, it may be 15, it may be 25. Hopefully it's not 25, but you know, it could be. Whatever the case may be, all right, your height is going to come from delta x. Your first and last base are the most extreme, A and B, okay? They only appear once, but then all the other bases in between get added together twice. Remember, these bases are all going to be delta x apart, okay? So to get from one to the next, you just have to add that delta x, okay? So let's do an example. Please write down y equals x squared plus 1. Our interval is 1 to 2. So y equals x squared plus 1. Our interval is 1 to 2. And we're going to have 6 subintervals. So we're going to have 6 trapezoids. Okay, so go ahead and calculate delta x. What's delta x?
1/6.
1/6. Okay. Okay, because we take 2 minus 1, 1 divided by 6. All right. So for our area, for a trapezoid, we take 1/2 times the height. What is our height? 1/6. Times. We're going to sum up our bases. So our first base occurs at 1. So the function value at 1. And I'm going to write them like this, and then we'll figure out what all those values are. Where is our next base at? What x value? 7/6, right? We're all 1/6 apart. So our first base occurs at 1. Our next base occurs at 7/6. It happens twice. We have to add 2 of our next base of 8/6, 2 of our next base of 9/6, 2 of our next base of 10/6, 2 of our next base of 11/6, and then only 1 of our last base f of 2. Okay, now here's something I want you to recognize. Okay, when we were doing our rectangular approximations, how many numbers were in the parentheses? Number of rectangles, right? How many numbers are in this parentheses? One more, because we have to start at our starting point and end there. So you're going to have one extra number in your parentheses compared to how many trapezoids you have, because we are talking about base 1 and base 2, base 1 and base 2, base 1 and base 2. Okay, so if that helps you, I know some of us kind of like to be organized in that fashion, like, oh, do I have the right number of numbers here? Okay, that maybe will help you. Okay. Like I said before, in your work, you may want to keep them as fractions. So in f of 7/6, I would like to see you write it down as 85/36. F of 8/6, I would like you to write down as 25/9. All right, so if you, in fraction form, we get 721 over 216, which is approximately 3.338. I would accept either answer. However, keeping them in fraction form while you're doing your work is going to be helpful that you don't have rounding errors at the end. Okay. All right. If you are watching at home, I apologize for the freeze. Okay. How do you feel about trapezoids? Feel okay? Got to do some practice. Hey, guess what? You get a worksheet today. That's exciting. All right. What I would like you to do is draw this table. I don't care if you write the words, but I need you to draw this table with those specific values. Okay, so let's talk like real life situations here, right? Soon enough, I will explain to you what area under the curve can give to us, but for right now, let's just talk about how to find it, okay? If you are in science class and you're collecting data, it's not going to always match a perfect curve like x squared plus 1, okay? It's going to be rough, right? So instead of maybe trying to like take our data and fit a curve to it, we can take our data and use this concept of rectangles or trapezoids to find the area under our curve. Okay, so here are some data values. We collected data every 1/2 unit, whatever that unit may be. Or monthly time, who knows? And I want to find the area under the curve. Okay. So our interval is 0 to 3, and we are going to use 3 rectangles or trapezoids. How far apart? What's our delta x? Okay. So sometimes this is what I like to do. I have a rectangle that stretches from I have a rectangle that stretches from 0 to 1, and then I have a rectangle that stretches from 1 to 2, and then a rectangle that stretches from 2 to 3. Okay? So now, if we are doing left endpoint approximations, then our area, okay, how would we calculate it? The width of each of our rectangles is 1. Okay? The height of our first rectangle would be 2, because on the left of this rectangle, our height is 2. Plus, our second rectangle would stretch from 1 to 2. Its height would be 6. And then our third rectangle stretches from 2 to 3. Its height would be 4. Same set of data, same width. Right endpoint approximation. Our width is still 1, but now this first rectangle would have a height of 6. Right?
6.
We're on the right side of the end of our rectangle. 4 would be what? Yeah. From 1 to 2, what's our height? 4, because that's on the right side there. And from 2 to 3, our height would be 5. That's the right end of that rectangle. Okay? So here are areas 15. Okay? Same set of data, same blah, blah, blah. Now let's try midpoint approximations. Okay, our rectangles still have width of 1, but now this first rectangle, its height would be what? 4, because that's the middle. From 1 to 2, our height would be 7, because that's the height of 1.5. And from 2 to 3, our height would be 1, because the height at 2.5 is 1. So here we have an area as well. And finally, we're going to do some trapezoids. Okay, so our area, first we write 1/2 times the height, 1, times our first base, 2, plus 2 times our second base, 6, plus 2 times our next base, 4, plus we're now coming to our last base, so we only want one of them. So our area here. Okay, you have a worksheet today, which I'll post. What I'm going to post online, I'll post a blank worksheet in case you lose it. But then I'll also post only answers. If you have questions tomorrow, we can go through any of it, but I'm only going to put the answers up because I don't want you to just copy down what I have. Okay. There are 6 problems. The first 4 are straight up trapezoid. The 5th problem and the 6th problem are some tabular data practice. Seniors, this is a reminder, you have your picture today. It was supposed to be yesterday, it was supposed to be in September, but now it's going to be.
Yeah, I was really confused, and they were like, hey, it's not happening today, in September, and then I was like, so when's it happening? January. I didn't know for like last week.
So,